Hello everyone, welcome to my YouTube channel SGKmistry Lectures. In this video, I'll be continuing with my explanation on crystal field theory. So in my previous video, I had given an introduction. Hello everyone, welcome to my YouTube channel SGKmistry Lectures. In this video, I'll be explaining about crystal field theory. In my previous video, I had given an introduction to this particular topic. So let us try to understand more about this successful theory of explanation of the geometry of the coordination compounds, that is crystal field theory. So let us start with understanding about octahedral complexes. So in an octahedral complex, already we know that the central metal is surrounded by 6 ligands. So you can see here, this is the arrangement. 4 ligands will be in one plane and 2 ligands will be, one of them will be above the plane and one of them will be below the plane. So this is the arrangement of the ligands in an octahedral field or in the octahedral complex. So now what happens during the crystal field splitting in an octahedral complex? Now we know that here the ligands approach the central metal ion or the central metal atom along the axis. So you can see this is the z-axis, you can see this is the x-axis, and this is the y-axis, which are perpendicular to each other. And these 6 ligands, whatever are there in the octahedral complex, they approach the central metal ion or the central metal atom along the axis or in the direction of these axes, in the direction of these 3 axes. So now you can see that as we've already know, in the previous video, I have already explained about the arrangement of the d orbitals in the with respect to these x, y, and z axis, right? So now we know that T2g orbitals and EG orbitals, these are the sets of orbitals in case of octahedral complexes. T2g orbitals, we know that this particular set consists of dxy, dyz, and dzx orbitals, whereas EG set consists of dx square minus y square and dz square orbitals. So this I have already explained in detail. So now we know that here, while looking at these orbitals itself, it is very clear. See, dxy, yz, and zx. These orbitals are oriented in between the axis. Between, now, if I'm talking about dxy, it is oriented between the x and y axis, and so on. Okay, whereas dx square minus y square and dz square, these are the d orbitals which are oriented in the direction of the axis. So now we know that these ligands are approaching the metal atom or the metal ion in the direction of the axis. So of course, these orbitals will have more energy now because the ligands are approaching. So there will be repulsion between the negative charges, right? The electrons and the ligands, as well as the electrons that are present in these orbitals. So of course, these orbitals will have higher energy now in the presence of ligands. Whereas these orbitals, which are present in between the axes, which are oriented in between the axes, they will have lower energy. So now let us look into how these d orbitals will split in the presence of an octahedral complex or in the presence of an octahedral field, okay, to be more precise. So this is the how the d orbitals are present in the free ion. So hypothetically speaking, now in the presence of a spherical crystal field, that is, if there is a metal and the crystal field is just spherical, hypothetically speaking, the spherical crystal field, if it is present, then all the d orbitals will have equal energy, which is actually, we are only, this is just for taken for reference purpose, but in the actual case, either there will be octahedral or tetrahedral or square planar. So that is what happens in the actual case. Now, here we know that when the ligands are approaching in the octahedral complex, when I'm talking about, so here, as I've already explained, these two orbitals will have higher energy now, the EG set of orbitals, whereas the T2G set of orbitals will have lower energy. So one set of triply degenerate orbitals will be there and another set of doubly degenerate. Degenerate is nothing but the orbitals having same energy. So here this is doubly degenerate. There are two orbitals with same energy, whereas this is triply degenerate where these 3 orbitals have equal energy. Now, how the electrons will be distributed in these different orbitals, that is what we have to understand. So now let us talk about octahedral splitting when I'm talking about the first 3 or electrons. So now we know that in an octahedral field, first these 5d orbitals will be having the similar same energy. So I'm talking about in the spherical field, in the hypothetical spherical field. So now what happens in the presence of an octahedral field, when the ligands are approaching, so we know that 2 orbitals will have higher energy and 3 orbitals will have lower energy. So this is T2g and this is Eg, right? So now what happens? Let us talk about when 1 electron is present, then it will come here. When there are 2 electrons, another electron will come here. When there are 3 electrons, of course, it will first fill the lower orbitals, because all these orbitals in the T2g set, they have the same energy and they have the lower energy. So always we know that according to the Aufbau principle, as well as how the electrons are filling in the orbital, so all these rules we already know. So electrons will first fill whenever there are equal energy orbitals. First the electrons will be singly occupied and then there will be pairing. And one more thing we have to remember is that whenever there are orbitals of lower energy, first the electrons will fill into the lower energy and then only they will go to the higher energy, right? So first, when we are talking about the first 3 electrons that are filling in these orbitals, there is no confusion. Directly we can say that the 3 electrons will occupy in this way. Now the question comes when we are talking about the 4th electron. So 4th electron, whether the 4th electron will go here or whether there will be pairing. So this is what we have to understand. So in this case, we have to talk about one more type of energy, which is called as pairing energy. So pairing energy is nothing but it is the energy required for the pairing of 2 electrons that will be paired in the same orbital. Okay, that is called as pairing energy. So let us talk about more about this particular thing, that is how this pairing occurs and how the electrons will be distributed based on the magnitude of the pairing energy as well as the magnitude of the splitting, the octahedral splitting that is there. So this delta O is nothing but, so here we have seen this particular energy gap, what you can see between the T2g and Eg orbitals, that is represented as delta O. Okay, so now let us talk about this delta O as well as the pairing energy. Suppose if delta O is greater than the pairing energy. Okay, so let me just explain. So there are 5 d orbitals. So in the presence of the ligands, so we have here 2 orbitals above and 3 orbitals below here, right? So now this is nothing but delta O. Okay, this is delta O. And now we are talking about the pairing energy. So now let us talk about the condition of D4. That is, there are 4 electrons in the d orbitals. Okay, so now 1, 2, 3. 3 electrons will be filled in this way. There is no question here. There is no confusion, or there are no other conditions that are prevailing here. Now talking about the 4th electron. Suppose if delta O is greater than pairing energy, if this particular gap is higher, okay, if the gap between the T2g, this is nothing but T2g and this is Eg, if the gap between these 2 set of orbitals is very high, then you can just imagine, you can just understand the situation here. Of course, the 4th electron cannot jump to the higher energy, right? Because the gap is very high here. So what does it do? Instead of jumping to the higher energy level, it will undergo pairing here. Okay, so this is what happens. Suppose if delta O is greater than pairing energy, then the configuration will be in the T2g orbitals, there will be 4 electrons, and in the Eg orbitals, there is no electron, so TEG 0. So this is the configuration that is occurring when the delta O, okay, is greater than pairing energy. Now let us talk about the second situation. Okay, there are first of all 5 orbitals. Okay, now there is Eg here and there is T2g here. This is T2g and this is Eg. Right. Let us talk about, there are 4 electrons in the d orbitals. Okay, in the beginning, again, I'm talking about D4 configuration. So first what happens? 3 electrons will fill here. That is what happens in the beginning. Now we are talking about the 4th electron. Here, pairing energy is higher than the delta O. Okay, so here the splitting energy, the gap between this, we are talking about delta O. Okay, but the pairing energy is higher here. That means the energy required for pairing of electrons is very high when compared to the gap between the set of orbitals. So of course, now what does the electron do? Instead of undergoing pairing, it will go to the higher energy level like this, because pairing energy is higher here. Okay, so now what happens? The configuration in this case will be T2G. Here there are 3 electrons, so T2G3 and EG1. Okay, so this is what happens when pairing energy is higher than the delta O. So now talking about tetrahedral complexes. So already we have understood in detail about what happens in an octahedral complex. Let us talk about tetrahedral complexes. Once you have understood octahedral complexes, it is very easy to understand, but just there are a few changes. When I'm talking about tetrahedral arrangement in a particular complex, tetrahedral complex, so metal atom or the metal ion will be in the center. So when I'm talking about the comparison with that of the geometry of a cube, you can see that the ligands are placed in the alternative corners of the cube. See, here there is one ligand. So this corner is left as such. There is one ligand. Again, there is no ligand here. So alternative corners of the cube. Okay, now again there are axes. You can see x-axis, y-axis, and z-axis. You can see that the position of these ligands, okay, they are not exactly in the direction of the axis. See, the axes are here and the ligands, the position of the ligands is, it's different when compared to the direction of the axis. So here the ligands are more of in between the axis rather than in the direction of the axis. Right. So now here what happens? It is the opposite to what is happening in an octahedral field. Okay. So here the E orbitals, especially here we are not talking about EG or T2G. We are just naming them as E and T2 orbitals. Okay. So E orbitals, which consists of dx square minus y square and dz square. Now we know that these two orbitals are in the direction of the axis. Right. Now, since these two orbitals are in the direction of the axis, of course, their energy will decrease because the ligands are approaching in between the axis. Right. So these T2 orbitals, which consist of dxy, dzx, and dyz, they will have higher energy now. Okay. So now let us talk about what happens during the splitting. So of course, now T2 will have higher energy when compared to that of the E orbital. So dx square minus y square and dz square will have lower energy here, whereas dxy, dyz, and dzx will have higher energy. So here T2 will be of higher energy, E set of orbitals will have lower energy. Now, when I'm comparing the tetrahedral and octahedral complexes, the splitting that is taking place here, that when I'm talking about the delta value, okay, here for tetrahedral, we write delta T. For octahedral, we are talking about delta O, which we have already discussed about delta O in much detail. Right. Now, when I'm comparing this delta T and delta O, of course, delta O is having a higher magnitude when compared to that of delta T. What are the reasons? First reason is very simple. We know that in octahedral complexes, there are 6 ligands, whereas in tetrahedral complexes, there are only 4 ligands. So of course, the repulsion or whatever, when we are talking about interaction between the ligands and the d orbitals of the metal, so here, in case of octahedral complexes, it is higher. So here, the splitting is also higher. The magnitude is also higher. So delta O is larger, or the magnitude is larger. And one more reason is, as I've already told, in case of octahedral complexes, the ligands are approaching the metal in the direction of the axis. Right, in the direction of the axis. So of course, what happens because of this, the orbitals and the ligands, they are arranged in the same direction. Here, what happens? Now, when I'm talking about dz square or dx square minus y square, here, these two orbitals are present in the direction of the axis and the ligands are also approaching in that direction. Whereas in case of tetrahedral, it is not exactly in the direction of dxy or dzx or yz, but here the ligands are approaching in between the axis, right? Not exactly in the direction of these ligands as such. Whereas in case of octahedral complexes, the interaction is much intense. Okay, so because of this delta O, the magnitude is much higher when compared to that of delta T. The relationship between these two quantities is given as delta T, or these two delta values is given as delta T is equal to 4 by 9 into delta O. Now, talking about distribution of electrons in the tetrahedral crystal field, whatever the splitting takes place and how the electrons are arranged. We already know that delta T is having a lower magnitude, right, when compared to that of the delta O. So, of course, when I'm talking about the splitting of d orbitals, the two orbitals will be here, three orbitals will be above, right? Here, this particular splitting, the delta T value, when I'm talking about, it is very less, right? The gap is lesser. So now when I'm talking about two electrons, of course, they will be present here. The third electron, it always tries to go to the higher energy like this before pairing. Okay, so the pairing energy is more in case of delta T. So instead of undergoing pairing here, the third electron will go to the higher energy. That is, here this is, we know that this is T2 and this is E. So here the electron will go to the higher energy. So here, next fourth electron will come here, fifth will come here. After that only here there will be pairing. Okay, so this is what happens in a tetrahedral complex. So very rarely there will be pairing in the beginning itself, but most of the complexes, the third electron will go to the higher energy. Okay, now when I'm talking about the splitting of d orbitals, the electrons that are entering into the d orbitals, all these when we're talking about, we should understand something called as CFSE. That is nothing but crystal field stabilization energy. How to calculate that? So let us consider the octahedral splitting. So first there are degenerate d orbitals. Then this is in the case of the spherical field. Okay, this also we now here this is what happens. The spherical field that is there. Now what happens in the presence of an octahedral field? We know that splitting occurs. Two orbitals will have higher energy. The three orbitals will have their energy will decrease. So the energy will be decreased when compared to that of this hypothetical or the barycenter what I'm talking about. So here T2G will be having lower energy, EG will be having higher energy. And this gap, when you compare it with that of the barycenter, this is nothing with the barycenter what we're talking about. So this energy, when we are talking about EG, it increases in energy by 0.6 delta O. This particular energy gap, the value is 0.6 delta O, and this energy gap is 0.4 delta O. That is the three orbitals that are forming the T2G set, they will decrease in energy by 0.4 delta O. Okay, or you can also call it as 4dq. This you can call it as 6dq. Okay, you can represent it in either of this way, either this or either this. Okay, now based on this we can calculate the crystal field stabilization energy. Now it can also be represented in this way in the form of ratios. So here the two orbitals are increasing energy by 3 by 5 delta O. These three orbitals are decreasing energy by 2 by 5 delta O. Okay, so this is the different ways, or these are the different ways of representing. Okay, either 0.6 and 0.4 you can call, or 6 dq or 4 dq, or this 3 by 5 delta O or 2 by 5 delta O. Okay, now how to calculate this crystal field stabilization energy? So there is a particular formula. You can just look into this. You can note this. So crystal field stabilization energy is given by minus 0.4 into n into T2G into delta O plus 0.6 into n into EG into delta O. Now, what is this n into T2G and n into EG? This is nothing but n represents the number. So, number of electrons in T2G orbitals. Here also n is number of electrons present in the EG orbitals. Okay. So, why is 0.4 and 0.6? I think by now it is very clear, because this is this 0.6 delta naught. Okay, and here there is 0.4 delta naught. So based on that we are calculating. Here why we are talking about minus? Because the energy has been decreased here for T2G orbitals. Here we are talking about plus sign between the for 0.6, because energy is increased here for the EG orbital. So that's why plus and minus. Okay, so here you can also calculate by this way. So any one of the formula you can remember. so that you can calculate the CFSE. Okay. So now let us talk about tetrahedral. So it is the opposite, of course, because we have already discussed about the tetrahedral crystal field splitting. So CFSE in tetrahedral field is given by zero point 0.4 into number of electrons in the T2 orbitals minus 0.6 into number of electrons in the E orbitals. Okay, so you can refer any of these formula. So now let us take some examples and try to understand this in detail. Okay, one second. Yeah. So let us talk about the octahedral complex where the number of electrons is D2. Okay. So we know that the 5 electrons are there. So let us talk about the 5 orbitals are there and the 2 electrons are there. So here we have three orbitals in the here which have lower energy and 2 orbitals which have higher energy. Right. So here we have this T2G and this we have EG. Right. So this is the barycenter. So here we know that this is 0.4 delta naught. This is 0.6 delta naught. Right. So now when I'm talking about the CFSE, crystal field stabilization energy here. So when I'm talking about D2, of course, the 2 electrons will be filled here. Right. So there are 2 electrons here. So I'm talking about here minus 0.4 into number of electrons in the T2G orbitals. There are 2, right? So 2 here plus 0.6 into number of electrons in the EG. Here there are no electrons in the EG orbital, so 0. So minus 0.4 into 2. Okay. So minus 0.4 into 2 is minus 0.8. Okay. And here minus plus 0.6 into 0 is 0. So the crystal field stabilization energy here is minus 0.8. Okay. So now let us talk about crystal field splitting in the square planar complexes. So here, when I'm talking about the octahedral complex, we know that this is the arrangement. So there are, so if I take X as the ligands, okay, so these 4 ligands are in one plane, and these 2 ligands, out of these 2 ligands, one is above the plane and one is below the plane. So in a square planar complex, these 2 ligands are removed. That is, these 2 ligands which are present along the z-axis, they are removed off so that we have only the square planar complex. So this is what is the actual scenario. Okay. So 2 trans ligands located along the z-axis are removed from an octahedral field to get the square planar complex. Now, when the ligands are approaching through this axis, so very simple to understand, see, along the z-axis, the ligands are removed. So, of course, among the 5d orbitals, okay, we know that 5d orbitals are dxy, dyz, dzx, dx square minus y square, and dz square. Right. Whichever orbitals have the z in them. Okay. Here there is dyz, here there is dzx, and here there is dz square. So very simple, you have to understand, since the ligands are removed along the z-axis. So of course here there is no repulsion. If there is no repulsion, the energy is lesser. Remember this simple formula, more is the repulsion, more is the energy. Okay. So here there is no repulsion because there are no ligands as such here. So now, of course, what happens if there are no ligands, there are no repulsion between the negative charges or the electrons. So here, these orbitals will have lower energy. The energy of these orbitals will decrease. Okay, so you can easily see here, see dz square energy is lesser when compared to that of the dx square minus y square. And here you can see dzx and dyz orbitals have lower energy when compared to that of the dxy. So this is what happens during the square planar during the formation of a square planar complex and how the crystal field splitting takes place. Okay, so now let us try to understand in a simple way about high spin and low spin complexes. Now, when I'm talking about strong field ligands, about this I've already explained what are strong field ligands in my previous video. So if you have not watched, you can just watch and try to understand about this. So examples for strong field ligands, we know that cyano ligands, carbonyl ligands, all these are strong field ligands. So when these ligands are present, Okay, when the complex consists of these ligands, they will cause large splitting of the d orbitals. That means here the delta value will be very high. Okay, so now let us talk about, first of all, there are 5 orbitals. Okay, and these 2 orbitals will be here, 3 orbitals will be here. This is, let me talk about octahedral splitting, so T2G and EG. So whenever these ligands are present, cyano or CO or carbonyl ligands, which are the strong field ligands, they cause this large splitting of the orbitals. So in this case, now let us talk about how the electrons will be filled. So of course, if the delta value is very large, what happens? The fourth electron, instead of going to the higher energy, it will undergo pairing because the gap is very high, right? So it will not go to the higher energy level. Instead, the fourth electron will pair up. So let us look into the example. So here there is the nitro ligand, which is a strong field ligand, NO2 minus, okay, nitrito ligand. So now in this particular complex, okay, so what happens? It has 5 electrons. This particular complex has 5 electrons. So now see here, 5, 1, 2, 3, 4, 5. There are 5 electrons. Now, how these electrons will fill into these particular orbitals? That is what we have to understand. Now, 3 electrons will fill here, right? Now, since this delta value is very high, the fourth electron will not jump to the higher energy level. Instead, it undergoes pairing. So, 5 electrons will be present in T2G level. So, the configuration will be T2G5 EG0. Okay, this is what happens. Now, such complexes are called as low spin complexes. Okay, this is, we have to understand here, because you can see that the number of unpaired electrons that are present here, in this particular case, it is only 1. Okay, in such cases, in such low spin complexes, the number of unpaired electrons that are present is lower. So you can just remember this way, so that it is easy for you to understand as well as easy for you to remember. Okay, so now let us look into what are high spin complexes. Okay, we know that these ligands, F minus, I minus, okay, bromo ligand, aqua ligand, all these are weak field ligands which cause a lower splitting. Okay, the magnitude of delta is lower whenever these are present. So in this case, what happens? Instead of pairing up of electrons, the electrons will jump to the higher energy level. Okay, let us look into this particular complex. Okay, F minus is a weak field ligand. Okay, so again, there are 5 electrons here. So here I'm talking about the 5d orbitals, the 2 orbitals above, that is the EG orbitals and T2G orbitals. Okay, now how to identify how many electrons are there? That is, I hope you know, but if you're not aware, let me just explain. FeF6 3 minus. This is the complex we are talking about. So let us first talk about, let us try to understand the oxidation state of the metal. So let me take it as X plus F minus, okay, the ligands, whatever are there. So here there are 6 fluoro, so minus 1 into 6. I'm talking about the oxidation state now. That is equal to minus 3. So X minus 6 is equal to minus 3. So X is equal to minus 3 plus 6. X is equal to plus 3. So iron has the oxidation state of plus 3 here. In the ferric state, it is present. So iron, the atomic number is 26. So argon is 18. Then we have 3d and 4s. So if it has 2 electrons here, 6 electrons here. This is about when iron is in the zero oxidation state, okay, which is in the neutral atom, what we are talking about. Here there are, the iron is present is in plus 3 state. So there are 3 electrons which are lost from iron, because we know that whenever any metal atom is in plus state, in the positive oxidation state, it has lost electrons, right? So plus 3 means it has lost 3 electrons. So of course, the configuration will be argon 18, 2 electrons from 4s is lost, and 1 electron from the 3d orbital is lost. So of course, now it will be 3d5. So you can see there are 5 electrons in the d orbitals, right? So let me show the 5 electrons here, 3, 4, 5. Okay, now how the electrons will be filled in the crystal field due to the crystal field splitting, how will be the arrangement? So 3 electrons, of course, no doubt, it will be in the T2G level. Now, what about the fourth electron? Here, the delta value is lesser because fluoro is a weak field ligand. So, since the gap is lesser, so the fourth electron will go to the higher energy level. Okay, and fifth electron will be here. So, now the configuration will be T2G3 EG2. Okay, so this is what happens. Now you can see the number of unpaired electrons is very high here. There are 5 unpaired electrons. Okay, so easy to remember since there are more unpaired electrons here. Just by looking into the configuration itself, you can identify it is a high spin complex. Right. Okay. So this is about crystal field the splitting as well as crystal field theory. Now, what are the limitations? Of course, every theory will have its own limitations. Let us talk about limitations of crystal field theory. Although it explains so many different concepts, but still it could not explain a few things. First of all, it considers metal and ligand bond as electrostatic, purely electrostatic, but it could not explain about the partial covalent character that is present. Okay, and it only explains about the metal orbitals, what happens during the splitting, all these cases, the octahedral, tetrahedral field, how the d orbitals in the metals will split. But it is not explaining about why in certain cases, why the certain ligands, why there is much splitting, as well as in case of certain ligands the splitting, the delta value is lower. All these things were not explained in detail. Okay, it could not explain the interactions with the metal orbitals, that is with the ligands. And it cannot also explain the bonding in case of metal carbonyls. Okay, so about all these things we'll be learning in the further lectures. Okay, so for now, I think it is understood about what are the limitations of this particular theory and also how it explained about the geometry in case of the octahedral, tetrahedral, as well as square planar complexes, about how the splitting occurs as well as how the electrons are distributed. So thank you so much. If you want to know more about the magnetic properties as well as the color of the complexes based on crystal field theory, I have already uploaded the videos in these topics. It is already there in the profile, so you can go through that to understand the further applications of crystal field theory. Thank you for watching the video. So subscribe my channel for further more informative videos. Thank you.